So today we'll talk about the direct mapped cache. In our last class, we have seen that the architecture of an associative cache memory, and in case of associative cache memory, we have seen that the main memory address is divided into two components. One we have said is the block number, and other one is the byte specification within the block. But the problem in case of associative memory is that the hardware requirement is too high, because all the tag memory locations are to be compared with the block number in parallel. So I have to have a number of comparators. Comparators nothing but set of XOR gates followed by a NOR gate. So I'll have a number of comparators which is equal to the number of tag memory locations or the cache memory blocks you have within the cache memory. Now, this direct mapped cache concept is slightly different. In case of associative memory, we have assumed that any block from the main memory can be placed in any of the cache memory block, or cache memory block we will refer to as cache line. So any block of the main memory can be placed in any of the cache lines in case of associative memory. In case of direct mapped memory, for a particular block in the main memory, the cache line in which that block can be put is specific. Okay. So in case of direct mapped cache, the main memory address will be divided like this. I'll have few number of bits which as before specifies a particular byte within a block. Okay. And the other field, which in case of associative memory we have said that is a block identification. In that case, this field, in case of direct mapped memory, this field is again divided into two fields. One field is specified as a group, and the other field is specified as tag. So coming back to our earlier example, where we have assumed that we have 16-bit main memory address, and 3-bit was given as byte identification within a block, and the 13 bits, these 13 bits were specified as tag in case of associative memory. In this case, let us assume that the group identification will be 5 bits. Okay. And sorry, group identification, let us assume that it will have 8 bits, and tag identification will be 5 bits. So total is 16 bits as before. Okay. And now you find that every block in the main memory, if I say that every block is a unit, so every block in the main memory will have two component address. One is the tag address and other one is the group address. Okay. That means a number of blocks in the main memory are grouped together to form a particular group. Similarly, a number of blocks in the main memory are identified by the same tag number. So if you take intersection of these two, a particular group number and a particular tag number, that identifies a particular block in the main memory. Okay. So because there are two component addresses for every block in the main memory, I can logically put the main memory in the form of a two-dimensional array. So something like this. So these are the main memory blocks. Okay. Now, every row in this block will identify a particular group, and every column in this block will identify a particular tag. Okay. So because we have group identification which consists of 8 bits, that means with the help of 8 bits we can identify one of 256 groups. So if I put the group numbers here, this is group number 0, this is group number 1, group number 2, this way, the last one will be group number 255. Okay, and the tag, every tag is identified by 5 bits. That means one of 32 different tags can be uniquely identified by these tag bits. So I put the tag numbers in the horizontal direction. So this is tag number 0, tag number 1. So like this it will continue. The last one will be tag number 31. Okay, and these are the block numbers. I call this is block number 0, block number 1, block number 2. This will be block number 255. This is block number 256, 257. So this way it will continue. This one will be block number, say, 7936. If you calculate, it will come to 7936, and this will be 8191. Okay. So all these blocks, block number 0, block number 256, okay, block number 512, this way block number 7936, all of them belong to the same group, and it is group 0. Okay. Similarly, block number 1, block number 2, block number 3 up to block number 255, all of them belong to the same tag, and that is tag number 0. So when this tag field is 0, group field is also 0. That identifies this 0th block in the main memory. And 0th block contains 8 bytes. So out of this 0th block, which byte is required, that is specified by this byte number. Okay. So I logically put the main memory like this. And since I have so many groups, any block belonging to a particular group can only go to a particular cache line. Okay. So since I have 256 different groups, I will also have 256 different cache lines in the cache memory. So this is the cache memory, and in cache memory I'll have 256 cache lines. Okay. So this is cache line 0, this is cache line 1, cache line 2, this is cache line 255. As before, for every cache line, I have to have a valid invalid bit. So when a particular cache line contains a valid block of main memory data, main memory content, then the corresponding valid bit has to be 1, otherwise the valid bit will remain 0. Okay. And then finally, I'll have the tag memory. For every cache line, I have one tag memory. So you find that unlike in the earlier case, where every tag memory will have to have 13 bits, now every tag memory will have 5 bits. So this is tag memory. Okay. So now find that a particular group, any block belonging to a particular group, can come only to a particular cache line. So a block belonging to this group, 0th group, will come to cache line 1. A block belonging to group number 1 will come to cache line 0th group will come to cache line 0. Block belonging to the group number 1 will come to cache line 1. So like this it will continue, and any block belonging to group number 255 can only be placed in cache line 255 in the cache memory. Okay. So now if I assume that, say, block number 257 is placed in the cache memory. Okay. In that case, the corresponding valid bit will be equal to 1. This 257 block will come only here. Okay. So this is block number 257 will be contained in cache memory. The corresponding valid bit will be equal to 1, and the tag field will contain value 1, because this particular block belongs to tag number 1. So tag field will contain a value 1. Okay. Similarly, If 8191, this block is also in the cache memory, okay, in that case, this block 8191 will come to cache line 255. It cannot go anywhere else. Okay, the corresponding valid bit will be 1, and the tag memory field in this case will be 31. Okay, so given this type of organization, now let us see that what will be the architecture by which a byte from the cache memory can be extracted. So architecture now will be very simple. Here we have main memory address, which is broken into three components: byte, group, and tag. So this is byte, group, and tag. Okay. So first what I have to do is I have to identify the group which is being searched for, and this group identification will come from the main memory address itself. The total number of bits in this main memory address is 16, out of which the group field contains 8 bits. Okay. So if I want to identify a particular group, then what I have to do is this group field I have to feed to a decoder. The decoder in this case is 8 to 256 decoder. Okay. Now depending upon what is the bit pattern in this group field, one of the 256 outputs of the decoder will be high. All other outputs of the decoder will be low. Okay. Now what I have to do is I have to check that for that particular group identification whether the tag field matches with any of the tag memory content or not. So for that particular group which is specified in the group field, if the tag field also matches with one of the tag memory contents and the corresponding valid bit is also 1, then only it indicates that the data which is being asked for is present in the cache. Otherwise, the data is not available in the cache. Okay. So here I'll have the tag memory. I also have the valid bits. So the logic will be something like this. I will compare the content of the tag memory location with the tag field that is present. Okay. So this will pass through its buffer, and to activate the buffer, what I'll do is I'll take the ending of the corresponding valid bit and the corresponding output of the decoder. This decoder is giving 256 lines. So this is one of the 256 lines of the decoder which is active. So there are 256 lines. Okay. And output of the AND gate is used to activate this buffer. So if the AND gate output, if this AND gate output is 1, then only this tag memory content will be available at the output of the buffer. So I have to compare this buffer output with the content of the tag memory. So here what I have to have is a 5-bit comparator. Okay. Now the comparator output can give that either this tag content is not equal to this tag field content. So this is the case when they are not equal, and I can have another condition, another situation that they are equal. So only when the content of this tag memory is equal to the tag field in the main memory address, in that case I say that I have a hit. That means the data which is being asked for is available in the cache memory. Otherwise, this is a cache miss. So this will indicate a cache miss, and this will indicate a cache hit. Now, if I have a cache hit, then what I have to do is I have to extract the corresponding block from the main memory, and from the block I have to select the particular byte which is requested. So on this side, let me draw the cache memory. Which is having a number of blocks. Okay. So in case of cache hit, and this output is 1, then this data comes to a selector, or selector is nothing but a multiplexer, and one of the inputs of the multiplexer is selected by this byte field. Okay. And this is the output that goes to the CPU. So these are the tag memories, these are the valid bits, and these are the cache memories. Okay. So find that effectively what we have done. First, we are comparing the group field, trying to identify the group field with the help of 8 to 256 decoder. Okay. Now, depending upon the content of this group field, one of the 256 outputs of the decoder will be high, all other outputs will remain same. So I'll try to check that particular tag memory location corresponding to which the decoder output is high. Okay. So my logic is, if I find that I get a tag for which the group field is also matching, then I assume that the requested data or the requested block is available in the cache memory. Okay. So I make it an ANDing operation. The decoder output is ANDed with the corresponding valid bit. So if the valid bit is 1, this decoder output is also 1, then only I go for checking the tag bit. Okay. So if these two outputs are 1, that means the AND gate output is also 1, then this buffer is active. Tag bit, tag memory content comes to the comparator. In the comparator, you compare with the tag field which is there in the main memory address. If you find that this tag memory content is same as the tag field, then I say that the data is present in the cache memory. So I have a cache hit. If they are not same, then that is a cache miss. So only when we have a cache hit, okay, because this cache hit may arise from other uh, buffers also. Okay, because every tag memory content contains some value. Okay, so it may so happen that this condition is true for some other tag memory, whereas this output is not true. That is also possible. So I have to check that I have a tag hit, I have a cache hit, and at the same time this output is also true. That means this corresponding valid bit is 1, the group identification, that is also true. then only I will extract the corresponding cache block. So what I am doing is I am making an ANDing operation of this heat output from the comparator, equality output from the comparator, and the output of this AND gate, which is ANDing the valid bit with the decoder output. So only when both these conditions are high, then only I will take out the corresponding cache block again through this buffer. Okay, so here what I get is the entire cache line which contains 8 bytes. Out of these 8 bytes, I select out one particular byte by making use of this byte field. Okay. So the advantage that you get in this case over associative memory is that in case of associative memory, I had to have n number of comparators if there are n number of blocks in the cache memory. But in this case, that is replaced by only one comparator. Okay, so it is the same comparator which will be used for comparing the tag locations, all the tag memory locations. So what you have effectively is, because these are buffered, so outputs of all such buffered are connected together, because only one of the buffer will be active at a time. And the buffer which will be active, that is depending upon which decoder output, this decoder output is high. Other buffers will not be active. So only one data will reach this comparator from the tag memory location, which will be compared with this tag field in the main memory address. Okay. So effectively, the n number of comparators that we had to have in case of associative memory is replaced by only one comparator in case of direct memory. But what is the disadvantage? Because in this particular case, you have specified that a particular block in the main memory can only go to one cache line. It cannot go anywhere else. Okay. So the number of cache miss may increase. The number of data being taken out of the cache memory or put in the cache memory will also increase. Whereas in case of associative memory, since this block can reside anywhere in the cache line, so it is quite likely that at least one of the cache lines will be free whenever this block is to be placed in the cache memory. But here now, since this block can come only in this cache memory, the probability that this cache line will be occupied by some other block is very high. Okay. So that may lead to more number of cache miss, whereas in case of associative memory, the number of cache miss may be less. Okay. So what we should try for is a compromise. That means we want to have the advantage of both the associative memory and also the advantage of the direct memory. So that is what is known as set associative caches.
Corresponding to that tag field is high.
Yeah.
So, sir, why there is need to have another connection for that valid bit to access the location from the cache?
Right.
So we have used AND gate at the cache line.
Yeah.
So what's the need of this thing?
So it may so happen that the address that you have asked for, okay, maybe the group address, because always there will be some content within this tag memory location. Okay, so by mistake it may so happen that it is not this tag memory or this group identification which is active. It may so happen that I get the data from some other location in the cache memory and which matches with this particular tag field. So it may so happen, suppose this output of this comparator is active. Okay. So in case this output of the comparator is active, I will have similar such AND gate here, which will be ANDed with this valid bit. Now this valid bit and this active, they make the output of this corresponding AND gate high. That means content of this tag, okay, will be fed to the comparator. Right. So when content of this tag is fed to the comparator, but that is not the location that I am asking for. Okay, I am not asking for that location, I am asking for some other address. Okay, So in that case, this address which has been generated, corresponding to this address, the block does not reside in the in the cache memory. So the data that I will get is some other data, not the data that I am asking. So this AND gate ensures that both the tag and the group, they are identical, right? Then only I will extract this cache memory content. Otherwise, I will not extract it. Okay. So in case of set associative cache, what modification is done over this direct mapped cache is that instead of specifying a particular cache line in the cache memory where a block can go, a main memory block can go, we assign a set of cache lines where a particular block from the cache memory can go. Okay. So what we have is, in case of set associative cache, that we define a set of cache lines. Okay. So coming to the same configuration as before, we assume that again I have 16-bit main memory address, of which 3 bit will be used for byte identification, 5 bits for tag identification, and 8 bits for group identification. So I redraw that figure. So these are the main memory blocks: 0, 1, 2, 3, this is the 255, 256, and so on. Here I'll have number of groups 0, 1, 2 up to 255, and the tags 0, 1, 2 up to 31. Okay. In case of direct map cache, what I have said is that a block belonging to this group can only come in this cache line. Okay. Now in this example, let us assume that I have a cache which is twice the cache that I had in case of direct map cache. Okay. So in the earlier case, the cache memory had 255 cache lines. Now let me assume that instead of 256 cache lines, now let us assume that the cache memory has 512 cache lines. Okay. So the cache lines will be arranged like this. So I have 2 cache lines in any of which a block corresponding to this particular group can reside. So now this block 256, earlier case, the block 256 could go only to cache line 0. Okay. Now this block 256 can go to either this cache line or this cache line. Similarly, block 1 can go to either this cache line or this cache line. So I'll have a cache miss only when, if I find that block number 1 has to be brought into cache memory, okay, and both these cache lines are occupied by some other blocks. In earlier case, because I had only one cache line, so I would have a hit if I want to bring in this block number 1 and this cache line 1 is occupied. Okay. So now I have an option that in one of the 2 cache lines, I can place a particular block. Okay. So that will reduce the number of cache miss that I can have. So when I put this set of 2 cache lines, okay, which can contain a particular block in the main memory, this is called two-way set associative cache. Okay, I can increase the number of cache lines, or I can increase the cardinality of this set. Instead of having 2, I can have 3, I can have 4, I can have 5, and so on. So more the number of cache lines you put in a particular set, you will find that the number of cache hits will go on reducing, but at the cost of the number of comparators. In the earlier case, for direct mapped cache, I had only one comparator. In this case, set associative cache memory, because a block can contain in any of these two cache lines. So I have to compare both the tag fields corresponding to both the cache lines simultaneously with the tag field of the address that is generated. That means in this particular case, I need two comparators to achieve parallel comparison. In case of associative memory, what I had, if there are n number of cache lines in the main memory, so all the n tag memories are to be compared with the tag field of the main memory simultaneously, main memory address simultaneously. So I had to have n number of comparators. In case of direct mapped memory, that was reduced to one comparator because a particular block of the main memory can go to only a particular cache line. Okay, so only one comparison is needed. In case of two-way cache, since the block can go in any of these two cache lines, so corresponding to every such cache line, I'll have a tag memory. Corresponding to every such cache line, I'll have a valid indirect field. Okay, so now the tag field that is specified in a particular main memory address, that has to be compared to both the tag memories for that particular set. And if I want to make this comparison parallelly, that means I have to have two number of comparators. Okay, one for comparing, say, tag field corresponding to this cache line with the tag field of the address. The other one for comparing tag field corresponding to this cache line with the same tag field in the main memory address. Okay, if I have a three-way set associative cache, I have to have three comparators. Five-way set associative cache, I will have five comparators. Okay, so in the extreme case, when I have a large number of such sets, so that is the set associative, when any block can go anywhere in the cache memory. That is one extreme. The other extreme is direct mapped cache. And in case of set associative, what we have is in between, where we reduce the hardware, but at the same time, I try to maintain the flexibility of the associative cache to some extent. So here I'll have a compromise between the number of cache misses that I will encounter and the amount of hardware that has to be incorporated. Okay, and I hope you can draw a similar such schematic diagram for this two-way cache memory or even for an n-way cache memory. So in that case, what you have to do is this valid bit will be replaced by two valid bits. The tag memory field will also be replaced by two tag memory fields. This part will remain same because the group identification, which is 8-bit, that has to go to 8256 decoder. Out of this, I'll have one of the outputs to be active. That output has to be fed to two such AND gates. Okay. One of the inputs to the AND gates will come from one valid bit. The input of the other AND gate will come from the other valid bit belonging to the same set. Okay. Outputs of those two AND gates will enable two such buffers. One buffer will get the input of one tag field. The other buffer will get the input from the other tag memory of the same set. Okay. So at the output side, I get two tag memory contents. They will go to two different comparators. This tag field will go to the other inputs of both the comparators. Okay. On the output side, both the comparators, I can have a situation that both the comparators give a condition not equal. So only when both the comparators indicate that there is a cache miss, that is a true cache miss. That means this cache miss output of both the comparators are to be ANDed together to indicate that there is a cache miss. Cache hit will be one of the two comparators gives an output 1. That means the hit output of both the comparators are to be odd to indicate there is a hit. Okay. Now when there is a hit, the other part will be again similar to this. So only thing is the whole thing will be duplicated. So the amount of hardware that you need is twice the amount of hardware that you need in case of direct mapped cache, but naturally it is much less than what you need in case of an associative cache. Okay. So we
If we do it serially,
if you do it
serially with only one comparator for two-way set associative.
yeah, if you do it with only one comparator, in that case there has to be a sequential circuit here. So the job which I can do in only one clock period, that has to be expanded to 2 clock periods.
Just a matter of nanoseconds.
See, in case of cache memory, what we are trying to do is we are trying to make the operation very fast. Okay, so having just one more comparator may not be that costly, but the time may be costly. Okay, but that is feasible. It is not what you are saying is impossible. That is also feasible. But having just one more comparator or two more comparators may not be that costly when you go for VLSI implementation. So with this, we stop today.